Hello and welcome back to Assembly Language Programming AT89C51 using Keil software. In this video, I'll explain how to generate rectangular waveform using Keil. Before writing the program, I just want you to explain few steps which are to be understood for writing the program. So the first one is how to generate the rectangular waveform. Suppose you are given a frequency of f, the rectangular waveform of a frequency f, and a duty cycle DC, and the crystal frequency is given. Now we have to generate the waveform. So the three steps that are to be followed is step 1. So this is your rectangular waveform. This is the time period T1 and this is T2. So the total time period for that one complete cycle is Tc. Now in step 1, we will calculate T1, T2 and Tc. So given the frequency f of the rectangular waveform, Tc we can calculate as Tc is equal to 1 by f. Next is, so duty cycle is given. Duty cycle is nothing but duty cycle is equal to T1 by total cycle Tc into 100. So from this we can calculate T1 as Tc is given. Tc we already calculated, so we can calculate T1. The third step is, we know that the total time period to complete one cycle Tc is equal to T1 plus T2. Therefore, from this, we can calculate T2 as Tc minus T1. So in the first step, we'll calculate Tc. Next, substitute Dc and Tc because Dc is given, and then calculate T1. And because the time taken to complete one cycle is sum of T1 plus T2. T1 is called pulse width and T2 is called space width. So total time period is T1 plus T2. So from this we know T1, Tc already we calculated. So then calculate T2 is equal to Tc minus T1. So all three are calculated. T1, T2 and Tc. Next, in the next step is, so this is the square waveform, rectangular waveform, sorry. And this is called off time of the rectangular waveform. And this is called on time of the rectangular waveform. So how much time the waveform should be in the high state and how much time period the waveform should be in the off state, we have to calculate. So step 2, on state. So to calculate the on state, we have to consider the crystal frequency because in the problem already crystal frequency will be given. So consider that generally the crystal frequency will be 11.0592 and the microprocessor divides this frequency into with the 12 and then we get a frequency of f, then calculate t is equal to 1 by f. Once we get t, now we can calculate on time as so we know what is T1 from the step 1. So T1 by this time period, calculate, let it be some x, a number, a decimal number, right? Then convert x, that is, we have to subtract this x from 65,536 minus x. Then we'll get a decimal called y. What is this 65,536? We all know that the 16-bit numbers will start with 000 and count up to FFF. FF corresponds to 65,535, right? And for C, so the counter counts from 00 to FFF, and then it overflows. If we add 1, then it again goes to 00. So it becomes 65,536. So we have to subtract this decimal number from 65,536. We'll get a decimal number 1. Now convert this decimal number. Convert the decimal number to equivalent hexadecimal. Then we'll get a number, for example, like F, B, suppose C, B. Equivalent of this number, suppose we get like this. Now this is called the lower byte and this is called the higher byte. Now we have, y is the time, on time period, on time, the time for which the rectangular waveform should be in the high state, at that time period is called y. And it will be in a 16-bit rotation, and the lower byte is called TL1, upper byte is called TH1. So this is for the on time, right? So to get the on time, divide T1 by T. You know how to get T. From the crystal frequency, first measure F, then 1 by F will be given T. T1 we already know, divide that, we'll get a number. That number should be subtracted from 65,536. I told you why you have to subtract from the 65,536. Then you'll get a decimal number. If you convert this decimal number to equivalent hexadecimal number, you will get some number just like this. As an example, I have given this. Then this will be the on time of the rectangular. Similarly, we'll calculate the off time. So step 3, off time. So to get off time, divide T2 by T. Here let it be some x, and then subtract from 65,536 minus x. We'll get a decimal number called y and convert y to equivalent hexadecimal number. And let us suppose this hexadecimal number will be FE32. And this will be the lower byte and this will be the higher byte. This will be off time. So we have seen how to calculate on time and off time. Now we can write the program. And before writing the program, let me tell you that AT89C has a timer, right? There are 2 timers, right? Timer 0 and timer 1. So timer 0 has 4 bits and timer 1 has 4 bits. So this is timer 1 and this is timer 0. So you all know this bit is called M0, M1, M0, C by T bar and gate. Similarly for timer 1 also M1, mode 1, mode 0, and then C by T bar and gate. So we want to use a timer for the programming. I want to use timer 1, and in timer 1 I want to go for the mode 1 operation. So you all know there are 4 modes, 0, 0, 0, 1 and 0, 1. Why I prefer this mode is, in this mode the microcontroller operates as 16-bit mode, because the timer on time and off time are 16-bit byte. Hence I have chosen this mode selection. So I'm using timer 1 in mode 1. So I can write this in the register. I'm not using timer 0, so I'll initialize all bits as 0. And here I'm using mode 1, so it is 0, 1, and other bits are 0, 0. So if you write the equivalent, this is 0001, that is 1, 0001, that is 10H. So in the T mod register, we have to initialize with 10H. Why? Because it indicates that we are using timer 1 in mode 1 operation. So the waveform now will have, so the waveform, the rectangular waveform looks like this, with on time of FBCB and off time of, so I told you what the off time, that it be FEC3, 2, right? So we have converted time into hexadecimal. And then the T mod register, we have to initialize with 10. And then we can use any port to look for the output waveform. So these are the points you have to remember before going to the program. Now let us go to the program. Before going to the program, that we are ready. First thing is we have to find out TC, then T1 and T2. That is this pulse with the T1 and space with the T2. We have to find out, and next we have to find on time, and then we have to find off time, and then we have to initialize the T mod register with the 10H, indicating we are using timer 1 in mode 1 operation. Why we are choosing mode 1? In mode 1 is 16-bit number. So if we use mode 0, it will be 13-bit. Because a microcontroller, here we are using a 16-bit microcontroller. Then we have to use as mode 1. So this is the preparation for the programming. I hope you all understood, and also I hope you understood what is this value, because the counter is a 16-bit timers. They start from 00 to FFF, the maximum number. And if you want to get back to 000, you have to add 1 to it. So this I have converted into decimal number. So the equivalent of 6FFF is 65,535 plus 1, that is 65,536. From this, I have subtracted this value, T2 by T1 value, so that you get a number. And we have to convert again this number to the hexadecimal number to get on time and time. For on time, it is T1 by T, and for off time, it is T2 by T. And T we get from the crystal frequency. So that crystal frequency should be divided by 12, and then we have to find the inverse of the frequency to get T. Now let us go to Keil and write the program. So go to project, click on new microvision project, and write rectangle wave, right? Save. So it's already exists, it's okay. Save. Go to HTML, click on AT89C51, click on OK. No. So target is created. Now create a new file. Go to File, New. Now we have to type the program. So just type the program, start the program. Type ORG 0000H. Next. First, we have to initialize T mod register to 10. I told you why this we have chosen 10. Right? Next, we have to move first the on time lower byte, right, to TL1 and TH1. So first we'll go to TL1, TL1, comma. So for on time, we have chosen FBCB. So lower byte will be CB. You can go for hash CB H. Then similarly move TH1, comma, hash FP, H, subdecimal number. So we have moved the lower by to TL1, higher by to TH1, that is on time, right? Next is we have to set the port. I want to go with the port number 1.3 to check the rectangular output. So to see the output, we have to go, we have to select the port and I have chosen P1.3. Now set the timer register, set P TR. Now, so as I told you, the timer starts counting from the number, from this number FBCD and goes up to FFF. And after FFF, it goes to 0, 0, 0. Once it goes to 0, 0, the counter stops counting. So we have to check that. So that we have to write a loop called jump if not bit TF1. And then this loop has to be repeated until it counts up to FFF and goes to 0, 0. So loop 1. So the loop will continue until it reaches to 0, 0, 0. Next, so this is the on time. Now we have to go with the off time. So for that, clear TR1, clear TR1. Now we can write the same program because this is for the off time, right? And then here the number, I showed the hexadecimal number I'm using as FP. And then the higher bit, lower bit is 32. I have chosen, or you can go for 34. I think you want 32. And then FE we have chosen for the off time. And here, because from the high state, it has to go to the low state. So you have to use here CPL, complement output at P1. Again, set to PTR1. Now, again, it has to count from FP32 to FFF, and then it has to go to 0, 0. So it will check up to FFF. Once it goes to 0, then it will come down. So we have to loop 2 because already loop 1 we have used, loop 2, and again clear. And then because this is on time, right? And this is off time. Now you want to repeat the rectangular waveform for number of time cycles, right? So for that, you can repeat this. So S jump again, where again you can repeat the same steps, right? To get a continuous rectangular wave. So again, on time, off time, and then end. So this is the program. Now let us save this program first by save rectangular 1.asm. Extension we have to give, click on save. Now add to the target file, go click on plus sign, right click on source group 1, add files to group, and choose rectangular 1.asm. So your file will be added to the target. Add, close. So you can click on plus sign to check whether file is being added to the project. Next step is build the target. Go to project, click on build target. So there are some errors here. Let us see what are the errors. Two, 3, 4, 11. Here we forgot to give comma. 3, we can write the 0 here. We also please put 0. give as 0 CPH. In the 11 also, with the 0. So instead of giving FE30, you can give it to 0. Okay. Let us check again. Go to project, interpret. Now there are 0 errors and 0, 1. So when we are giving the numbers, let's put 0 before that, right? That's it. So this is the program and there are no errors or warnings. Now go to debug. Click on start and stop debug session. Click OK. Now we have to see the waveform, right? Where to see the waveform? For that, click on this icon, logic analyzer window, and then go to setup. Here we have to initialize the port. So click on this icon. Now here write P1.3. That is the port 1 bit 3, right? 1.3 close. Now you can start the simulation, but that click on this icon. So a rectangular waveform has been generated. So this is a procedure for simulating or generating the rectangular waveform using Keil. This is the program. So first we have to initialize the Q-mod register with 10H. Now the on time and off time lower byte and upper byte you give. Set the port under this is a port we are using as an output port, P1.3. Set the timer 1 because we are using timer 1. Set the TR1. And then TF1, you have to keep on checking the overflow flag because the counter counts from this number FBCB to FFF. And once it reaches to 000, the loops stops and then comes down. Then you have to clear again the timer 1 and overflow flag 1 to load the off timer to the lower byte and the higher byte. Now this load the lower byte of the off time and upper byte. And then we have to complement the code because it is a high state. Now it has to go to the low state. So use CPL complement. Again set the timer 1. Again check the overflow flag until it goes up to FFF. And then once it reaches to 000, it will end. Then this loop ends. And then again clear TR1, TF1. And then this procedure has to be repeated to get continuous rectangular waveform. For that, use SJump again. So it will move, so it will start again on the on time. So to get a continuous waveform. And to view the output waveform, you have to click on this icon called logic analyzer window. And then you have to go to setup part. And then here, click on this icon. So you get a block, type the code we have used in the program and click close. And then click on this to run the program. Once you are done, you can close this and get back to the main program. I hope you all understood.